Recorded. All right. So thank you so much for being on, Shirley. We really appreciate you being here and being able to talk about this particular topic. I know that this has been something that a lot of people have had questions about for a long time, and a lot of us, especially in public health, are very interested in this particular topic as it relates to SARS-CoV-2 and to other diseases as well. So I think with that, if you don't mind, I'll turn it over to you, and you can give an introduction of yourself and start presenting.
Great. Yeah. Thank you so much for having me. I obviously think this is a very exciting topic as well. And I think one of the main goals with this project was really to make something that was accessible to the people who most need it. So I'm really excited to be here and in touch with some potential users of a method like this. And I know there are lots of different methods. And so hopefully, as you said, Logan, there can be a little bit learned from all the different methods and something useful can become of it. So yeah, nice to meet all of you. I actually see a few familiar faces on the call, which is great. My name is Shirley. I am currently a project scientist at Scripps Research. And a lot of this work was done during my postdoc at Johns Hopkins. And I have a background in pathogen genomics. And like all of you, one of the questions that just kept coming up in our work was, how do we know if we've sampled enough to answer specific questions? And so this is one approach to that. I also just wanted to mention that I am totally happy to take questions during the talk if those come up, especially when I start to get into the mathy things. So please feel free to stop me at any time. I'm happy to engage. I really hope this is a discussion and that I can learn as much from you all in terms of what is useful as you learn here. So great. So I just wanted to start out kind of setting the scene for what the specific question we were trying to answer with these sample size calculations. Because I think one of the things that became really clear to us as we embarked on this was that sample size calculations is a really broad category, and the number of sequences or samples you need to figure something out to conduct surveillance really depends on the question that you are trying to answer or what you're trying to learn from the data. And so I just want to emphasize that this strategy is specific for answering specific types of questions. Because this project was kind of born of the COVID-19 pandemic, the questions that we were trying to answer, I think, are going to be very familiar and very relevant to today's world. And one of the questions that we thought just kept coming up over and over was, if you have a variant or if you have a mutation of interest and you're trying to track that in a population, how do you know if you're measuring that prevalence accurately? And so in this example on this slide, we have, for example, we sequence some samples or we do a PCR on day 3, and we see that everything we look at belongs to a particular variant or has a particular mutation that we're tracking. Are we sure that that is the only one in our population? Or is it possible that perhaps we didn't sample enough in order to capture something else? So that was really one of the questions that motivated this work. And then a very similar but slightly different question is, what if we actually see 2 and we see them at some percentage, one's at 50% and others 50%? Is that an accurate reflection of what the proportions are in the population? So hopefully a lot of you are very familiar with these types of questions and have already been trying to answer them with your data. And that, this question of what is the sample size needed is very familiar. So hopefully we can start to get at answering that today. So as I already kind of alluded to, this question can kind of be defined as a detection question, right? Can we detect something new if something comes into our population of interest or a specific geographic area? And also a prevalence question. And they're similar, but like a little bit different. So I just wanted to make an early distinction between them. And I think one of the key components of answering this sampling question is taking a moment to think about where do the samples we sequence come from? And here I'm talking about sequencing because I think that is a very common way to detect a variant of concern or to detect something, but I think this method could be applied to any way to distinguish different pathogen variants, different mutations, whether that's a targeted PCR or whole genome sequencing. Sequence is just a shortened name for all of that. And I think it's really important to consider where these samples come from, because that's going to help us understand what goes into this prevalence calculation that we're going to get from these samples. So we tried to kind of conceptualize what is this process and what are the biases in this process. So we kind of divided up our samples in 3 populations, where the first one here on the left is all of the infections in the population. And then there's only some of them actually get detected. And there are all sorts of interesting sources of bias here, right, that determine who or what sample actually gets detected, right? So you can have things like who gets tested, whether there are people with asymptomatic infections that don't get tested, what is the sensitivity of your test that's using, are you missing cases? All sorts of factors there that can take a pretty large pool of infections and reduce that to a much smaller pool of samples that could feasibly be selected for sequencing or some sort of testing. And then there's the other side of the process where you have this pool of sampling, and for a whole bunch of reasons, you're probably not going to get sequences out of all of them. So, you might be limited in resources or in funding or in equipment to do enough samples, or you might have some samples that are low quality and just don't generate good enough sequence or whatever other kinds of data you need to detect a variant. And this can certainly bias what your prevalence estimate might be. So even if you start with some percentage here, 10% in your detected infections, by some random chance, if you only sequence some of them, your outcome might only say you have 5% in your population, and that's wrong. And so I think one of the questions we wanted to get at is, how do we know if that's wrong, or what's the likelihood that our estimate is correct based on the number of samples? So hopefully so far, all of this setting the stage has been rather familiar to you, but please feel free to stop me if you have any questions. And now I'll kind of talk about what we did to tackle this problem. And I think a lot of what we have done to tackle it has been somewhat similar to the approaches others have taken, including the CDC that we were talking about, specifically because this right side of this equation is kind of a solved problem, right? It's binomial sampling theory, if you are familiar with it, which basically means there's some pretty basic math that already exists that can tell you if you sample some fraction of a population, your estimate is going to be correct to some degree. And that's pretty well-established math, I would say. And you can think of it as, if you have like a coin flip and there's some percentage that you're going to get heads, if you flip the coin how many times, what's your estimate going to be? And how is your estimate going to get more and more correct with more flips of the coin? It's the same theory that we can apply to this question. And so this aspect, this binomial, has been taken and run with by lots of different people. Did somebody just chime in?
Yeah, I have a question if you don't mind.
Sure.
So the sort of going from infections to detected infections, the change in, say, the orange here could either be owing to some bias in detectability or also random chance. Is that right?
Yeah.
And it's also possible that what gets sequenced is going to be affected by the nature of the given sample, right? Some
Yeah, absolutely.
And so you could actually have a correlation between sort of a carryover, right, of that bias that's caused by the characteristics of the particular sample that goes sort of all the way from infections through to sequencing.
Yes, and I think I think if that's what you're getting at here, where you might start with like a true population and then your samples are biased to begin with. So even if you sampled every single one of these, you'd still get the wrong answer. Is that what you're getting at?
Yeah, I think so. So I guess I'm just asking, are you, maybe I'm jumping ahead, but that sort of is a sort of a bias that's going to be actually correlated through these different steps. Is that something you try to address?
Yes.
Okay, thank you.
Yeah. No, I will get there. And if I don't get there clearly enough, please bring it up again, because I think it's a really important point that, like, you know, if this pool, this detected infections is biased in the first place, like it doesn't matter how many of the samples you pick. You could pick every single one of them and your prevalence estimate would still be wrong if this pool is biased. So yeah, that's definitely something that we were thinking about. Thanks for that. So yeah, I think kind of starting to get at that, and hopefully the next slide will kind of put it all together, is this sort of left side of the equation, if you will, is, I think, at least in a public health context, the interesting part, right? Like here are all of these factors that have nothing to do with like how many I pick, and everything to do with all the different things that could bias what shows up in your lab that can be chosen. And that's, you know, I can think of, 12 different things that can bias that, and I'm sure you all could think of way more. But we wanted a way to kind of build a simple model that takes into account some of these major sources of biases, but build something that was like modular and could be adapted for different scenarios. So if, for example, you had a known source of bias that isn't captured in the model we built, it would be really easy to kind of stick it in there without trying to re-establish this whole sampling framework. And as I've alluded to, here's our model. It looks complicated, but it's actually quite simple. And I'm not going to spend too much time on the like intricacies of the math and the equations. But I think the take-home message is, if we imagine this picture as this compartmental model, we can see that basically we have the same three categories. We have the infections at the beginning. We have all this stuff that can affect what shows up in your lab that you can select for sequencing. And then we have a few different things that determines what actually is a sequence or what is an infection that can be identified as a specific variant. So I think getting at the previous question, we kind of consider both of these halves together, and all of these things that affect this ultimately also infect the G, or the characterized infections at the end. They're not separate processes, but they're really, one affects the other, and all those biases do get carried through to the end. And without going into defining every variable, I'll just summarize that, in the case of SARS-CoV-2 or another pathogen you're trying to surveil, some of the most obvious sources of bias to us were, for example, the asymptomatic proportion. So what the probability is that infection is asymptomatic, the probability that an infection is tested at all, which we could divide into a probability of testing asymptomatics and a probability of testing symptomatic people, if we expect those to be different. The sensitivity of the test we're using to detect an infection. And also, I think something that we really wanted to account for was the probability that a sample is good quality in the first place. So for those of you doing sequencing, perhaps you're using like a CT cutoff, for example, to select samples that actually get put on the sequencer. And that could have a big source of bias. If one variant has much higher viral loads, and that means that your CT values are much lower, and so you're preferentially picking those samples to put on the sequencer, that's going to bias your result as well. So even though these are the ones that we identified, the setup of the model where each of these sources of biases kind of like is cumulative and plays into our final result makes it so that if you think of some other source of bias, you can kind of plug that into this same model. And what we did, and I promise it's about to get simpler, not more complicated, is we try to take all of these parameters or variables and actually put them into one number, which we summarize as the coefficient of detection, which maybe was a somewhat pompous phrase to choose for this, but we wanted to, summarize all of the different parameters that went into what is going to take this pool of infections and actually determine what is detected. And you'll see that everything on this slide has a little I subscript. And the reason that we did that is because we're thinking about everything here as proportions. So you're going to have one parameter value for each variant that you care about. So for example, your asymptomatic rate, you'll have a rate for your variant of concern and your rate for the rest of the population. And this is actually pretty important because when we work out all the math and all the numbers, what we find out is that what really matters in terms of calculating accurate prevalence is not the actual number here, but the ratio of the coefficients of detection between different variants or between the variant you care about and the rest of the population. And that's really important because it means that you don't actually need to estimate the values of all of these parameters, which I know is something that can be really difficult, right? Like, how do you calculate a asymptomatic testing rate? Like, that's a really hard number to come up with in a lot of cases. So here, because the only thing that matters is the ratio of these coefficients for different variants, it means that, for example, if this was the parameter, for example, that we said was the probability that a sample is high quality, meets some CT threshold, for example. If you don't know that percentage, but you can maybe make an assumption that that value would be the same between two variants, that number just totally drops out of the equation. You don't need to estimate it at all. Or similarly, like maybe you don't know the asymptomatic rate, but you expect it to be slightly higher for one variant. You don't actually need an accurate number. You just need to make sure that the ratio between the asymptomatic rate you assign for this variant and some other variant is approximately correct. So it basically decreases the number of parameters you need to care about because it only matters if they're different. Does that make sense? Because I hope that makes it feel like a little bit more manageable to apply a framework like this.
Hey, Shirley, this is Allie.
Hey, Allie.
Hey, this is wonderful, and I really like this. And I just had a question about, I totally hear what you're saying about like terms dropping out because you just care about the ratio, and that's makes it so much easier. But of course, there are going to be situations where we expect a difference between variants in terms of some of these terms, but we still won't know the actual sort of like threshold of that or like the scale of that difference. Is that a time when your recommendation would basically be to do sensitivity analyses with this at sort of different reasonable estimates of what you think that scale of difference is, and just kind of provide you a sort of, your sensitivity analysis on to what extent the variability in that scaling changes your estimates of prevalence?
Yeah, I think that's exactly right? Like, if you know that they might be different, and I think, one example I like to use is if you have something is more transmissible and you suspect that's because you have higher viral loads, and therefore, that's going to affect your like detection probability and your sample quality or something like that, you could play around with a few different ratios in this calculation and get kind of a spectrum of sample sizes you would need. And then you can make a decision, based on what's feasible or how conservative you want to be based on that. So you kind of have like a range to look at, if that makes sense.
Yeah, totally. Thank you.
Yeah, and I think that's an important point because, this is a simple model, right? It doesn't encompass every possible thing that could bias your sample. And the goal is not to, get exactly, down to the last sample, the correct sample size, but more to provide a framework so that if you need to sequence like 10 or 1,000 samples per week, because those are really different numbers. So the hope is kind of to provide a guidance of, am I in the right ballpark to be able to surveil this variant properly? And also, as we'll talk about in a moment, to go backwards, right? If you're like, I can only do 100 samples, that's all I have the resources for, you can calculate, okay, how likely is it that the estimate I got is actually correct? So kind of just trying to get sort of a reasonable way of constructing something, recognizing that we live in a very complicated, complex world, and it's really hard to estimate these parameters. So just moving on to like what this looks like, if you're somebody who likes reading plots, if you're able to estimate this coefficient of detection ratio, and you have some desired threshold where, for example, you want to detect a variant, you can basically calculate the number of sequences that might be required to say this with some degree of confidence. So I'm plotting here, I think 95% confidence. So to take a more concrete example, if you want to be able to detect a variant, any variant that's at least 2% in your population, and you know that your coefficient of detection ratio is 2, which means that maybe your variant of interest is, once you combine all the parameters, more likely to show up at that ratio, you can say, okay, I need 75 samples in order to detect a variant with at least 2% prevalence in the population. And to take the other more prevalence monitoring scenario, you can do that again here, where instead of saying, I want to be able to detect at least one of, the question is, I want to be able to say that my variant is at this prevalence within some precision, which I've set here to, I think, 20% of the true value, for example. And so you can do the same thing where you kind of figure out where you are. And again, you can use all the equations backwards so that if you know you only have 100 samples, you can say, this is how much confidence I have in my prevalence estimate. So this is hopefully starting to seem useful, let me know. But I think one of the things that keeps coming up in sample size calculations, and again, I know this is one method of many. I think a lot of people sort of took the binomial approach and then took different approaches to think about bias. So here's one of them. But sampling doesn't happen all at once. Like, I think it's pretty rare to be in a scenario where somebody's like, okay, I'm going to sequence 200 sequences and that's it, right? Sampling, variant detection, variant monitoring is a continuous process where maybe you're sequencing some number of samples per week or per month in order to keep track of different variants over time. So we tried to think about how this strategy could be extended to a continuous or an ongoing sampling process. And so that actually allows you to answer other types of questions as well. So you can say, instead of just wanting to detect a variant, how can I sample in order to detect it within 1 month of it entering my country or my state or my population? And another type of question could be, how do I make sure that I catch any variant before it gets to 2% prevalence in the population? So just thinking about those kinds of questions. And I'm not sure I made this clear enough at the beginning, but I just want to reiterate that, the idea is that this can be generalizable to any population that you're interested in, as long as you're able to estimate those ratios for the relevant population. So you can apply it on a city level or a country level or a small community level, as long as those parameter values that we talk about can be sort of estimated at the right ratios for the relevant populations. So again, we can kind of extend our method. I'm not going to go through the math, but basically we can get a similar sort of result that if we assume some underlying growth curve we can say we need this many sequences per day or per week to estimate variant prevalence or days, or how many days it's going to take to determine that we have this variant in our population. And we can adjust those estimates based on our coefficient of detection ratio. And so going back to Ali's question earlier, you might not actually know the underlying growth rate of your variant of interest, but we've now seen a lot of different examples of variants that have caused big waves or taken over in a population. So we can use those growth rates and maybe use this model in a few different scenarios, and each time get a sample size. And based on sort of that range of sample sizes, we can make a decision about whether we're going to take a really conservative approach or choose a sample size that's kind of in the middle of our estimates. So trying to make this really flexible to any sorts of underlying models that you want to test, and any questions that you have.
Hey, Shirley, I have a quick question. So when you talk about sampling strategy, I would think you're only talking about random sampling from basically you are treating the infections all equal and just do samplings at a random basis. But in real practice, at least in Minnesota, we sort of like divided the whole sampling into roughly two categories. One is the community testing, like anyone who feels symptomatic and just go to a testing sites and either a commercial lab or a community testing lab to get tested. And then there's another part that people feel sick enough that they're being hospitalized or even pass away because of that. And there's also a big portion of those. And different variant may cause different sort of like prevalence in those different communities. So have you take those into consideration, and come up with like a optimized sampling strategy out of it?
Yeah, that is a great question. And this idea of what if we don't have representative or random sampling is always the question, right? Like we're trying to account for as many sources of biases as we can, but like at the end of the day, we are assuming that all else is equal. I think in a scenario like that, where you're able to categorize your samples into really distinct groups, I wonder if you could sort of apply this method to each population separately, right? Because what really matters here is that you define the population for which you want to apply the method. So you could say, okay, maybe I want to apply this method to only people who are symptomatic or hospitalized for this infection. And then you would have to estimate, your asymptomatic rate would be 0 in this particular population. And you would estimate, for example, is the sample quality different between variants for that population? Or is the testing sensitivity different between variants within that population? And that would sort of let you monitor a variant in that population and to separately monitor it in a different population. And then you could kind of compare the results and see, are we seeing this variant increase in prevalence at both populations at the same time, or does it look different? That is sort of how I would think about it, to really just try to estimate your parameters separately rather than trying to like combine two sort of hand-selected populations together. Does that make sense or answer your question?
Yeah, I think so. Thank you.
Great. And so now what I was actually hoping to talk about a little bit and maybe make some of these ideas slightly more concrete is actually how you would do all of this. And we put together an R package that can be used to sort of put in some of these values and get out either an estimate of the confidence you would have in your estimate or the sample size you would need to achieve a particular confidence. You can kind of use it forwards or backwards. But we realized that a lot of the users may not regularly work in R, and it might be easier to have even something as straightforward as an Excel spreadsheet that you can, put a few numbers in and you get out a sample size calculation. So if this sounds interesting, I was just going to pull up the Excel spreadsheet and kind of walk through it for a few minutes and then kind of end with that and questions, if that sounds all right.
Yeah, I think that sounds great to us, and probably a lot of the users on this call do have some familiarity with R. So even if we have time
Great.
at the end, we might even be able to get into some of that as well.
Awesome. I see the chat make everybody use R. Okay, let me just share a different screen and then we will be ready to go. Okay, and yeah, I think, either R or this, they're both exactly the same calculation. So I think it was more just trying to reach as big of an audience of potential users as possible. And we've gotten some feedback that some people want a website or a Shiny app. And so all sorts of thoughts in terms of use cases and different users. So I think this might be easier to go through than the R package, just because we took the time to define everything very nicely in this colored spreadsheet format. Can you all see my screen? Great.
Yes.
I'll zoom in a little bit. But basically we have a tab here for each different question and forward or reverse. So we've divided it into the detection question with cross-sectional sampling, the prevalence question with cross-sectional sampling, and the detection question assuming periodic sampling. The prevalence question with periodic sampling is a little bit more complicated, so we can talk about it. It's not actually implemented in the spreadsheet, but it will be in the updated version of the paper to some extent. So in each tab, we've kind of defined all of these different parameters that we talked about. And if you were to click on a tab, each one has both the forward and the reverse option. So in this tab, which is the sample size calculation, you would put in all the parameters and get a number of samples to select for sequencing. Or you can use it the other way, where you put in the parameters and the number of samples that you can do, and it gives you the probability that you're actually going to detect a variant at the desired prevalence. And similarly, in the prevalence thing, it's the confidence in your prevalence estimate given a desired sample and precision. And what we've tried to do throughout these is sort of highlight that if values don't differ between a variant of interest and the rest of the population, you can just put 1, because it doesn't matter what value it is, because it's just the same. So I realize some of this font is pretty small, but for example, if you think that your probability that an infection is asymptomatic is the same between the variant you're tracking and everything else, you can put in just 1 for both of those and it doesn't affect that. And you can see that if, for example, we change the desired probability of detection, maybe we only care about being 80% correct, then we don't need as many samples, and that's what changed here. Or if we do want 95% probability, but we only care about samples that are above 5%, we can change that there, and that will change the number of samples needed as well. And we can do that again for the prevalence as well, where here we're talking about a desired prevalence that you want to be able to detect that, and then also some precision on that estimate. So if you want to make sure that you are within X% of the true value. And then finally, we have the periodic case where we're talking about samples per day, but you could also define a different time unit, and it could be per week or per month, however you want to define that. And that again depends on some growth parameters. And on the initial tab, we've provided some suggestions in terms of like default values that might make sense to start with. And then again, the purpose of this is to create something that helps you ballpark the number of samples that would be useful. So you could try a few different values in the range that you think might be possible and sort of compare those sample size estimates as part of, informing a larger sampling decision that might be based on this or other methods as well. So I think I'll pause there. If there are like specific questions or specific things that I should show here, I'm happy to take a moment to do that, or just answer general questions.
There were a few questions that were in the chat, so maybe we can take a look at some of those.
Sure.
So it looks like, what is the line between observed frequency and actual frequency? Where does the ratio fit in the coefficient of detection equation? Oh, I think that this was related to when you were presenting. And so do you plug the ratio in the equation, or does it replace the coefficient?
Yeah, I'm happy to pull that slide up, but I think basically the coefficient is calculated from all of these different parameters. Maybe it's a little bit more clear to see it in the spreadsheet here. So if you tweak these parameters, you can automatically calculate the coefficient of detection ratio, and that's what's used in this final sample size calculation. But as a user, probably what you would provide is the values of the parameters, either the correct ones or sort of artificial values that make the ratios between the individual parameters correct. Does that answer that question?
I'll let the person who asked it respond in the chat. Okay.
Thanks.
So I guess, yeah, I had a question on some of these things. So with these different things that you are changing now in order to calculate that coefficient of detection, are these things that, so I guess on that initial page, you had given some kind of suggested parameters for some of these things. But is this something that, is there something that's being calculated and like updated for kind of like different what am I trying to say? I guess like different variants. Is this being updated like based on kind of like empirical data that's coming from different variants, and that would be changing these default values? Or is this, I mean, I guess, is it something that we would just be kind of like estimating always?
Yeah, I think that's a great question. And I think, there are a lot of parameters that I think are really specific to the population that you're interested in, right? Like your percent testing, I mean, it's just going to vary so widely between different cities or different countries that I think it would be really difficult to maintain that list. But hopefully, the people who are actually involved in doing the testing are sort of thinking about those values and might have the best estimate. I do think that there are some parameters that we're starting to get a better sense of, like, for example, in the periodic sampling case, those growth rates, like, I think there's been a lot of work already on estimating, what did the growth curve look like for the alpha variant? What did it look like for the delta variant? So one of the, I think common use cases for that would be, plug in those growth rates for an alpha, for a delta, for an Omicron, and sort of compare what would your sampling need to be. And then you can kind of say, like, do I want to be prepared for an Omicron, or am I okay being prepared for a more alpha-like variant? And again, using that to inform, a sampling decision that's based on lots of different factors.
Thank you.
Yeah, I mean, it would be really nice if there was a website somewhere where you could just look it up. But I think, part of making this like modular and flexible to lots of different pathogens and scenarios means I think the people who are using it are going to be responsible for for thinking about some of those questions, but hopefully are the ones who are best poised to answer.
That makes a lot of sense. Yeah, I think I was maybe naively hoping that there would be kind of like an easy button to make our jobs a little bit easier, but yeah, I do think that that makes complete sense, that we're going to have to kind of take a lot of these things into account and use some of the data that we have available to us in order to be able to kind of come up with some of those values.
Hey, this is Allie again. I don't know that I have this question completely ideally formulated in my head, so sorry if this isn't clear. But you know, I think about sort of all of these different levels at which we're performing surveillance, and you know, the different remits of different jurisdictional levels of authority in public health for doing surveillance versus outbreak response and all of that. And I think that that means that we, apart from the biases, like the biological biases or things like that, that affect which samples are available for sequencing and then do get sequenced, there's also this sort of bias or just sort of pragmatism that shapes which samples we sequence as well. Mm-hmm. And that's variable depending on, you know, whether we're thinking at the county level or the state level or the federal level, right? And I just wonder if there would be a way from a surveillance system evaluation perspective to take some of these databases like NS3 or baseline, where like absolutely the bias processes that you're modeling still apply there, like for sure. But I'm wondering if there could be like a systemic effort probably done at the federal level that would help kind of counties or states or, you know, jurisdictions that maybe have more limited resources for doing this, understand what those coefficients of coefficients of detection are, like what, how far off are, you know, like how much more bias is in their data sets than is in the sort of gold standard representative data set that has its own biases. And I'm, you know, I think if there's folks from CDC on here who might do that work, feel free to chime in as well. I realize I'm totally spitballing, but I just think it might be really helpful to have, you know, have that sort of like external comparator for expected level of bias or expected coefficient of detection variability, and a sense of being able to benchmark what you're seeing in different areas against that. Is that crazy, or is that like reasonably doable?
I mean, I think it's a really cool idea. I don't know if I'm the best person to comment on it or facilitate it, but I think, yeah, like basically having somewhere where we can collect, like, I mean, this goes along with the previous question as well, right? Like in my community, town, country, city, whatever, here's the values I used, and here's the like coefficient of detection that I ended up with, just to kind of get a sense of like what numbers are reasonable. That's sort of what you're saying, right?
Yeah, I think so. And just like, you know, I think this is kind of a hard thing, but like, because there is bias in the gold standard representatively sampled data sets, but it would be nice to know, like, this is our best estimate of the true extent of bias that we would see. And I think it would be really helpful for, you know, groups who are, you know, maybe have less access to samples because they can only source them from like 3 hospitals or something like that, or because they have less access to sequencing, to actually have a measurable, tangible way to benchmark the degree of bias that is present in the samples that they end up sequencing. And I think it doesn't matter as much from an outbreak response perspective, right, where the goal is just to kind of sequence everything within your outbreak of interest. But I think it would be nice to know for groups that do representative sampling and are trying to maintain surveillance data sets with more limited capacity and at this smaller local level, to just know like how well are we doing compared to what we see, you know, in the gold standard representative data sets.
Yeah. No, I think that's a really cool idea. I think, that is one avenue that would be really exciting to see. I think, at like a much simpler, and just sticking within the framework that I've already thought about, is like, I think the sort of confidence, like the reverse, right? Like if you sequence this many samples, if you have, no biases at all, what is like sort of the best case scenario, right? So you could kind of play with the parameters and say, given that I'm only sequencing X, what's the most confidence I could possibly have given a fully representative data set? Because I think, that would be useful as well. Because I think, I've definitely been in a position where it's like, let's just do 100 samples. That seems reasonable, right? And like, even just having a like, what's the best you could possibly do with 100 samples, I think could be a useful frame of reference. But tell me if I'm off base on that.
No, I think that would be incredibly useful. Absolutely. Yeah. So this is such awesome work, Shirley. Thank you for doing it.
No, thanks for your questions. I feel like it's so much of this was really just trying to formalize like, what is the question that we're trying to answer, and how can we like circumscribe it? So more comments on that is like very useful, because I think that's half the battle. That was way harder than the math, I think.
Shirley, I have to commit that I throw my biostats knowledge out of the window a long time ago. But one thing I'm curious, what defines the variant in your calculation? Are we talking about alpha, beta, gamma, omicron kind of variant, or we're talking about B117, B117.1, those kind of thing?
So I think it can be however you want to define it, right? It can be alpha, beta, it can be something more specific. It can be like one mutation that you care about. I think the important thing is that there needs to be some way of thinking about or estimating which of those parameters you think would differ between the thing you care about, whether it's a mutation or alpha or B11624 or whatever, and the rest of the population. So I would say that, probably if your definition gets too narrow, like one mutation, in a lot of cases, there won't be enough evidence to say this is going to have, biological differences that would change these parameter values. But if you go really big, like alpha, then it gets a little bit easier to think about, okay, we know alpha was more transmissible, which could maybe affect this parameter and this parameter and this parameter. But it is designed to be flexible. It just requires you to define that upfront, if that makes sense.
Yeah, that totally makes sense, because one thing I was struggling is, if let's just say we detect something unusual and there's usually a delay between the actual time you find it versus the time that pangolin reacts and assign a new pangolin lineage, which is probably the most granular definition of lineage at the moment.
Right.
So I was struggling with that, like how would that define variant? So okay, that makes sense. Thank you.
Yeah, and I think another thing that, like, at least I think something like this or another calculation framework could be most useful is kind of choosing scenarios, right? Like if we get another Omicron, what is that going to look like, and what does our sampling need to look like to track that? And it's actually probably going to be a lot easier to track something like Omicron, because things that are more transmissible kind of get enriched in your sample. So it's often easier to detect them quickly and with reliable prevalence versus something that, is increasing in the population, but at a much slower rate. So you could kind of come up with like sampling frameworks that could be used in different scenarios and sort of choose between them if you don't know the biology of what you're tracking so far.
Well, but in real life scenario, I guess, do you think the lab will detect the quote unquote new variant first, or it's mostly based on epidemiological situation that, we suddenly have a surge at a certain area, like, the Omicron, or like the initial Alpha, we saw a surge in UK. And then you sort of like emphasize on sampling of that particular detection in order to quickly get the new variant out.
Yeah, I mean, I think as you said, like there's in the real world, that's often what happens. I think ideally what you will have done already is devised a sampling scheme that is useful for detecting variants, once they get to 2% probability. So that might happen before or after you notice a surge. And you probably won't know when you detect a variant at 2% that that's the one that's going to, suddenly take over, but you will have been able to detect it and say, you know what, we've actually been seeing that one since 3 weeks ago or whatever, like it will have been on your radar because you've designed a sampling strategy that enabled you to detect it with some confidence, rather than, you see the surge and you're like, well, the first time we detected it was today, but we didn't sequence enough last week to say with confidence if it was here or not.
That totally makes sense. Yeah, we saw it, we detected, we just didn't know it.
Exactly. Yeah, but at least that can help you answer questions of like, how long has it been here? How fast did it grow? Things like that.
That totally makes sense. Thank you.
Thanks.
Everyone, I'm just going to quickly jump in here and stop the recording because I know that we only have a few minutes left of this call and I won't be able to continue on, but I can transfer this over. So if people do want to stay on the call, they most certainly are welcome to. I don't know how much time you have, Shirlee, but I